Welcome again, everyone, to the Advanced OpenACC course. Thanks a lot for joining us today, and good morning, afternoon, or night to everyone. We're ready to go full speed on OpenACC. My name is Julia Levitas. I'm a product manager at the Tesla Group at NVIDIA, and we'll have to kick off this our first class. So let me start first with some logistics. First of all, every session of the course will be recording and available for you to review on our OpenACC courses page. To find it easily, just type in Advanced OpenACC course in Google, and the first page will be with the recording. All lines muted, just to make sure that the recording is crisp for everyone in audio during the actual webinar as well. So please submit your questions through the Q&A pod on the right-hand side towards the bottom of the screen. So we'll do our best to answer as many questions as we can, but in case we won't get to every single one of them, there will be office hour in a week, so on May 26th, and we will be covering questions there as well as more on the visual profiler. Then let me go quickly through the agenda for today and for the course overall. First of all, we do want to enable you to scale up your application on multiple GPUs during this course, as well as optimize with the profiler tools. So these are the main course objective for this class. The course itself consists of 2 classes. Today we're going to start with advanced profiling of OpenACC code. This is the first lecture. Every lecture is on Thursday. We're going to have lectures once a week at 9 a.m. Pacific time. Next lecture is office hour that will happen on May 26th. So we'll be answering the questions, plus we'll be covering some information on visual profiler. So I think it's enough of me talking, and let's get to work. I would like to introduce you to the instructor of the class today. Simon KIRCHHOFF is a solution architect at NVIDIA, and he is currently deeply involved in acceleration work of oil and gas codes, and has tremendous experience with OpenACC and CUDA. His passion is to help solve problems that combine visualization and HPC challenges. I would like also to add from my side that he is a great instructor and likes to answer a lot of questions. So don't be shy and send your questions in the chat pod, in the Q&A pod, sorry, and we will be answering them as we go, as well as at the end of their presentation. Okay, Ty, are you ready? We can get going.
Hi, thank you, Julia. Can you hear me okay?
Yes.
Very good, thank you. I really appreciate you taking time out of your day to participate in this session. Really, what we're focusing on here today is how you can be more productivity, how you can have more productivity with OpenACC, but by demonstrating it with some code that's very much similar to what's being used in environments today for seismic processing. The code that we've worked through here is actually available online and can be downloaded, as well as the data sets, and there's a corresponding lab that's been created for this. I'd like to recognize Ken Hester, solution architect at NVIDIA, for helping develop some of this content, and also Parit Kapadia from eInfochips also was a contributor early days for some of the content here. But before I go into the meat of the material, I wanted to do just a quick overview and a slight commercial. Again, there are different ways to accelerate your applications, and within an application, you can mix and match each of the ones that are listed here. If there's a library, like a cuFFT library, you can use that for drop-in acceleration. We will focus on OpenACC directives, and specifically today using a profile-driven approach, using these tools to really help get the maximum level of performance. And just a teaser, we're also going to show how you can get some portability. Once you've done some things with OpenACC, you can turn that and target not just NVIDIA GPUs, but multi-core. And then finally, you can also interact and mix in some portions of your code with programming languages like CUDA. It could be C or C++. And maybe if portability is your primary concern, a portion of your code could insert CUDA in very small areas and just limit the areas of non-portable nature. we see real customers doing that kind of thing, intermixing all these different technologies. But for this course, we're going to focus on real code with OpenACC directives and the profile-driven approach. So here's the commercial. There are different profiling tools available. There's a rich ecosystem that's out there. The mantra is to take the tool familiarity that you're already comfortable with and extend these tools to be able to allow you to profile and debug and iterate through a process using massively parallel environments. So they are supporting both the host CPU code profiling as well as GPU level profiling. The one that's highlighted in green here is the PGPROF. That's the tool from NVIDIA. You also may be familiar with NVPROF. The two are equivalent now. And basically, there's a command line and a GUI version of this to help you get deep understanding and knowledge of what's going on from within your application from a profile perspective. So just a little more on PGPROF, and again, this will be covered in the office hours next week, next Thursday. But this is a screenshot that shows some code being profiled that's OpenMP code, and as well as the timelines that you may have already been familiar with our visual profiler. So it's nice to have a nice GUI. Everything that's being shown in the GUI can also be collected on the command line. And on the right is a list of features that's available in PGPROF. So a screenshot that's shown here, again, it's not just for profiling GPU code. PGPROF can also allow you to investigate CPU details, but it's very much in the same style that you would for GPU. And in this case, that happens to be an OpenMP parallel code. And by clicking on a tab, as you're setting up to collect information and want to profile a particular application, you specify in the session where you want to collect and what kinds of things you want to collect. And if you want, you could just collect for CPU only, or you could collect for CPU and GPU both. In this case, they have collected with using CPU and on OpenMP. And if you hover your cursor over the glyph on the left that's showing the source code, you can pop some hints that talk about what the compiler is doing. So this is in a very rich interactive environment. To be able to display the source code, you double click down here on the swim mode. Let me see if I can bring up a laser. Here we go. So if you click on this module, double click here, it will display the source code here and associate it with it various hints to give you insight as to what's going on inside of the compiler in a very nice graphical form. Also, another example here is showing details like intensity, which is measuring the number of flops divided by the number of memory bandwidth. And that's an important factor as you're identifying critical regions. Having information about the intensity of that region helps guide you on where you really should spend your attention and focus. It also gives you some more detail about what's going on, what the compiler did within that particular area, in this case telling you that it activated a static block schedule. And then another scenario where it's actually even getting into lower level details about instruction optimizations or taking advantage of the vector SSE units, so forth and so on. So you can see that this tool is rich. It's not just for GPU profiling. Here is an example that you can switch and actually look on a particular case, and you can drill down and get a timeline, a visual inspection of what's going on in interacting with the host and with the device. And what's shown here on the left is the list of the percentage of time that's being spent in this particular area, and the routine within the function that's being called there, and specifically the line within that function that's being called there. So the profiler gives you a lot of information, and visually here, you might be looking for opportunities to overlap communication with computation. If you're spending enough time computing, it's possible that you could completely hide some of the latencies for communication. And this would also lead you toward using the async compiler clauses, the directive clauses as part of OpenACC. So there's a way to iterate and make changes and then look at the code, in this case, visually. So again, this is the end of the commercial. That there will be much more on the visual profiler for the office hours on May 26th. Now for the meat of the presentation here, it's broken out into these different subsections. So as I go through each subsection, I may pause and ask for questions along the way to make sure you're with me. But we are using a real code that's available in public domain with the data sets. We're going to walk through how to get a baseline performance, and then a strategy is to let the underlying system do some data motion. Identify where those critical regions are, put in some directives, but let the underlying system move the data and see what level of performance. We're lazy. Let's see what the system can give us. And there's restrictions, but those are going away with each release while you're working with managed memory. Then we'll take the output from the managed memory, because it's very verbose and telling you what it's doing for data motion, and use that as hints to help guide as we go back in and surgically insert those data directives within your code. There's a couple reasons to do that. One is it can give you the best performance, but two, it also helps you with portability. So once you've inserted those data directives, now you can target multi-core, which we'll share some of our results as well. So you don't just target NVIDIA GPUs. The managed memory option is only available on NVIDIA GPUs today. But when you put the data directives, then you can target not only NVIDIA GPUs, but multi-core. And then finally, at the end, we'll give you specific details of how you can download this code and do this in your own environment, or you can take our online lab as well. So let's get further into understanding of the application and how it fits. Why is this interesting, and why should this be something that might be pertinent for you to potentially use in your environment? As Julia said, my domain passion is oil and gas, and we work a lot with exploration and production companies. And this is a diagram showing different phases or aspects of the workflow in oil and gas. Just to acquire the data, it costs millions of dollars, and process the data costs millions of dollars. You really get into significant money, significant millions of dollars when you get down into the drilling the wells. So if you don't do this job of acquiring and processing the data right, it can result in a dry well, which means no return on investment. So there's big dollars at stake, and there's very important processes and workflow. GPUs are being used all throughout this workflow to accelerate the time to their answer, to reduce the amount of time that it takes that, and it is also helping build confidence in their drilling decisions. The area that we focused on for this particular lab is in processing of the seismic data. I'm going to take a little bit of time just to talk about how the data is acquired and then how that feeds into seismic processing, just to help orient you. Okay, so this is a diagram that is showing how the data is acquired in a marine setting or offshore setting. Think of this as a giant ultrasound experiment. What's different in an ultrasound, let's say if you have an ultrasound for your child, an unborn baby, pretty much know where the baby is and pretty much know what the baby might look like. The differences here are that you're on a much grander scale. Terabytes and terabytes of data come from a single survey, and we have no clue what's below the surface. And so what's going on here is this vessel is towing these streamers, vast streamers behind it that have what are called hydrophones, and they're sending sound waves through the Earth that are being recorded. And as those waves travel through the Earth, they bounce off of different reflectors. Different subsurface geology has different density of rocks, and as the waves bounce off of those densities, they get recorded at different times, and that's what's shown over here on the right. The time series data that comes back from one of these surveys is known as a shot record, and each one of these is a trace. The challenge is to be able to take this time data and try to figure out what the real subsurface looks like. And to do that, you need a number of different processes to enhance the signal and reduce the noise. So this is showing on the left just something that is exposed to the Earth. You've probably all seen these kinds of things called outcroppings, and it's showing, you know, various different layers that have dipping layers and they pinch out. There's different strata of rock. There's shale, sandstone, and if there were a survey done over this particular area, the results that come back after crunching through the data might look what's on the right. It's called the seismic reflection data. And interpreters will use this to try to justify to senior management why they're going to spend multi-millions of dollars to drill in this particular area, because we think there's hydrocarbons in that area. Now, the code that we're using for this is one of the processes to help with imaging here. This can also apply if you have workloads where you're doing any kind of time series analysis or any kind of signal processing or filtering or ray tracing. The same kinds of steps that we're going to go through to use profile-driven approach and OpenACC might be able to apply in your environment as well. So it's a well worth exercise to listen to how we went through this process. One thing that's important to know is you're collecting the data with this time series. You need to know how deep to drill. If so you're looking here in the time series of data. It's important to know how deep to drill. Some won't drill deep enough and they'll miss the workload completely. And so to do that, you have to use a velocity field to convert from time to depth. And different rocks have different velocity properties. Well, the industry, it uses simulation and models, and they've built these complex models that have a velocity model, and they have synthetic data sets. They're industry standard data sets. And you can download these data sets, and that's part of what we did for this exercise. So we already have the data set available for you, or the instructions at the end on how to do that. But the idea is to take your seismic algorithms that you're using to help generate the proper image at the proper depth and compare that against a known model. Again, ultimately, they want to improve confidence in their drilling decisions. So if you look at the processing flow, this is a typical case. On the left here is a diagram that shows, again, data coming in from the field after it's kind of been quality controlled. We're talking about terabytes, multi-terabytes of data coming in, and there's usually some pre-stack processing and post-stack processing. And if you'll notice, there's various different boxes that are part of this workflow to do filter, scaling. Basically, you're operating on time series data. And one of the big ones here is called migration. And migration is doing things like helping collapse these diffractions, because as the sound waves go through the Earth, they get diffracted in so many different ways. And it can distort where the true depth is of the field. And the other part of what the migration operation does is help you correctly position the dipping layers so that you do drill in the right area and not too far left, not too far right, and you drill deep enough. So migration is an extremely important part of the workflow. And the tool that's used most, every company in that's working in this space has a Kirchhoff migration. There's several different types of migration. One that's in vogue is reverse time migration. And we do really well with that, but for this particular case, we chose Kirchhoff migration. And there's an open source package from the Colorado School of Mines that is freely downloaded. It's called Seismic Unix, and it implements a lot of these functions that are shown on this chart for you, including a C module that does a Kirchhoff migration. That's the one we chose. So we downloaded the representative data set from here. We got the representative source code, the entire software package from here, and compiled it and went through our process. Before I forget, I want to let you know that we did this not only on Intel-based systems with GPUs attached to that, but we also took this entire Seismic Unix package and ported it to an open power system, an early version with GPUs, and early versions of the NVIDIA Portland tool chain. And we did a recompilation, and there's many modules in this package. Two of them caused our compiler to segfault. And after a day or two with working with our Portland team, we were able to fix those, and so we were able to compile completely around. And all of the OpenACC directives, including the data directives or using the underlying managed memory, just worked on the open power environment. So it was very, very nice transition. And we're now, I think, moving into the beta version of our tool chain, but that's a really exciting capability to be able to take this stuff and move it to different platforms. So to talk a little bit more about what's going on with the Kirchhoff migration, the name of the package inside of many of these modules is called SUKD MIG2D. And this is just a kind of pseudocode that gives you a sense of what is going on in the code. So from the main program, you obviously input the data set, but then they're updating what are called residual travel times. And this can actually take quite a bit of time on bigger data sets. For our particular case, it was less time. Then you go through this giant do-while loop, and in that do-while loop, you're calling a function called sum2, which is combining these travel time tables, updating them, getting random locations of energy and adding those together. So there's a lot of random I/O from a memory perspective. And then also you're calling this routine called MIG2D. And in that routine, there's a bunch of multiply nested for loops that are doing various signal processing things like low-pass filters, looking at amplitude. They're doing interpolation laterally and interpolation along depth. And then finally, you output that trace and go on to the next. So just to give you a sense for what the code looked like under the covers. Question is, how do I take this and make it work using the OpenACC tools? Well, we've devised a methodology. We call it APOD, for Assess, Parallelize, Optimize, and Deploy. And so we'll go through each one of these steps and talk about how it was being used with this specific code. First, let's look at the assess phase. This is a diagram. Yes, ma'am.
Let me interrupt for a second. There are not a lot of people who are familiar with oil and gas, and if you can, in a brief sentence, shortly say what seismic data is, that would be really helpful.
Okay. Yeah. So seismic data is it's a series of series of data that's collected in this process. So this is seismic. Each one of these, think of it if you have a giant data set, and each one has a record associated with it. In that record would have like a header, and then you would have information about all the time series data that you collected for that one record. And you just have multiple of these records all put together in a single data set. And it's also, so the seismic data is nothing more than associated time series data that's collected from these experiments that are acquired in the field. I hope that helps answer. So then, going back to the assess part of this, we went just used the CPU code and used PGPROF. When you fire up the PGPROF in the GUI, you can specify in the file session and determine, which different where the executable resides, what directory you're in, and what command line arguments. Tell it what data you would like to collect, and then you say go, and it just takes the binary and it runs through that, and out comes at the end a histogram on the right here that shows you where various time is being spent. And you can double click on that particular function. It brings up in the source area, and then you can do further investigation like we talked about earlier, just go through the iterative flow. You can also see the output from the console window. So as a result of running this through the profiler, sure enough, based on our pseudocode, a lot of time is spent, 79% of the time is spent in that MIG2D function, 8.5% of the time is spent in SUM2, and less than 1% is in resid. So we should definitely focus our attention in the optimized section of the code on the MIG2D. So this is kind of giving you an idea of what it's like for profiling and determining where the critical regions are. Well, let's check in. What's our results? For the baseline CPU only, given a smaller model size, this is limiting the area that you're processing of the data. On one core for an Intel platform, it took roughly around 218 seconds. As part of the lab that's associated with this, you will actually go through and run these experiments and be patient on that first go around, because it does take, somewhere in 3 to 5 minute range to actually go through that first stage. So that's it for the assess phase. Now I'm going to move now on to the parallelize phase. I'll pause here for a minute and see if there's some questions. Okay. I think we'll go on now. We'll just continue forward. All right, so now that we've identified the critical regions, the next thing to do is, why don't we let the system try to do the work for us? So the first thing we did is went in, and in the MIG2D routine, where 79% of the time is spent, we inserted a pragma directive around the outer loop for the ACC parallel 4. We also instructed the compiler to vectorize the inner loops by inserting pragma ACC loop on the inner loop of the routine for MIG2D. Now, there's an iterative process here where the compiler can actually tell you also if this is a candidate for parallelization, and there may be some other things that prevent parallelization. But in our case, that worked fine for MIG2D. Same with SUM2. When we went into SUM2, which again was about 8% of the time was spent there, the compiler did complain about this notion of loop carry dependence prevented vectorization. And so what we did in that case is went back and added the keywords restrict on various of the pointers. This is a hint that the developer gives to the compiler to say that, yes, this is not going to be an alias point. It really will reference it, or any of the factors associated with it. There's not aliasing associated with these pointers. So this is a very common technique to go in and add restrict keywords. And then we did the parallel AC4 on the outer loop and let the inner loop be parallelized by the compiler. Okay, so again, once we determined that next we focused on the reset function, And it also talked about some vectorization, that loop carry dependencies that would prevent vectorization. And so we went back there and we actually inserted in the inner loops the pragma ACC loop to instruct the compiler to go ahead. It's okay to go ahead and vectorize this loop. We studied this particular scenario where they're updating the travel times and determined that, yes, it was okay to have the compiler go in and instruct it to do the loop carry, do the vectorization for you automatically. Okay. So what I'd like to do is just show a slide here to talk a bit about, now that we've added these directives to the code, let's take advantage of unified memory. Previously, before we developed unified memory, you had separate memory spaces you had to worry about, the system memory and the GPU memory. With the introduction of unified memory, we make this as one addressable space. And further, we've developed over time the underlying system that can migrate data automatically behind the scenes from the host memory to the GPU. Now, in the current implementations with PCI Express and our modern day Tesla Kepler GPUs, Maxwell GPUs, there's some restrictions. And in the next generation with NVLink and with Pascal, we'll reduce those restrictions and give you even more capability to oversubscribe memory on the host side and have fine control on where memory placement is given here. That's using the CUDA 8 API. But for now, let's pretend we're geoscientists and we don't want to really get down into this detail. We want to just be able to use the tools to migrate pages for me. I know enough that, okay, I profiled it and I know there's a hotspot here, so I put in some pragmas, I put them in various other places. Now let's just go try to see if the underlying system can migrate pages for me. And the way you do that is you compile with this option TA=Tesla:managed. And that's an instruction to the compiler to allocate the memory as managed. And then when that's done, the underlying system today in the current implementation will, by default, page it over to the GPU, and only if it's needed, send it back to the CPU. You also have a series of restrictions about that. You can only do this if your data is being allocated off a heap. So if there's static allocations, that's not allowed. There's a host of other kinds of restrictions in today's environment, and that's documented pretty well in this link that's written by Michael Wolf at Portland. So again, the benefit, the reason you want to do this is we haven't inserted any data clauses. We've just gone in and inserted these parallel clauses, and we really haven't really looked at the data flow at all, right? And now we can, once we've done that, we can use the output from the compiler as well as from the profiler to see what's going on behind the scenes. And like I alluded to earlier, this is only going to get better when you get to Pascal and NVLink. We're removing hurdles along the way. So we did that. We just added these compiler directives around the loops. We compiled it with this Tesla managed option, and here's the results. Not too bad. Not too bad at all. In fact, as a geoscientist not having to worry about computer science, that's pretty good uplift right there. But can we do better? And again, remember, now that we've done that, this would only run on NVIDIA GPUs. That's only where the managed memory is available today. So there's an incentive to go in and add some data directives to give you supportability, but this could be good enough for a larger part of the community. Well, how do you go from managed memory to data directives? Get the verbose output from that compiler. Because when he was compiling with managed option, there was a lot of detail that was provided as to what he was doing associated with the data, what the compiler is doing associated with the data. So use that verbose output to help you. So this next section, I'll go into data directives. Let me pause for a moment and see if there's some questions. Let's see. The question about how much a gigabyte of the model size, how big the data size is for this particular case. For the test case that we're running, it's a pretty small data set. I'd say, I can't tell exactly, but it's pretty small. Suffice it to say that the production level field data is terabyte size in volume. And with these tools, you can limit the portion or the area of the survey that you're operating on. Okay, there was seeing this full code maybe, so let's see, what's the performance cost for using unified memory? That's a good question. So today's systems are paging across PCI Express. They're also lending toward having all the data reside on the GPU, and if it needs to go back to the CPU, there can be a pretty significant cost. So you do have to pay attention to that, and that's what the profiler can help you do, is help you identify the data motion that's being used by managed memory, and then you also use the hints to help guide you. So we'll go into more detail about that. Let's see. Are there advantages with NVLink to PowerPC systems? So yes, so the PowerPC has NVLink connections to the host as well as from the host to the GPU, and so that offers you a higher bandwidth link and also lower latencies. So yes, in future generations that do NVLink connections from PowerPC, you would get a benefit for using the underlying system to do demand paging. And so yeah, that's I think an answer to that. So I think that's some answers to some of the questions. There's some more that are coming in, and maybe we can get to all of those near the end of the session here or in our next session next week on the office hour. So let's talk a little bit more now that we've done the parallelize phase, let's go into the optimize phase. So what we do in this section is, again, use the compiler and compiling with the option managed, but then profile that managed binary. And again, like we say, look at the output from a profiler. So PGPROF in this case can be done at the command line, and you can report information out like this in the command line, or you can also do this from within the GUI. But this is actual output from this particular test case, and it's showing where the time is being spent, which is still in the MIG2D and the sum2 cases, as you would expect. But it's also giving you information about some of what's going on with the memory operations and how much time it's actually spent on this. Now that we instructed it to use managed memory, it's giving you input on how much time is being used in that function, and various other operations that you want to pay attention to in looking at the output from the profile data. Again, the other thing to look at is not just profiling the data, but also looking at the output from the compiler. So when you use this managed option here, the compiler is very verbose, and it gives you lots of interesting information. It tells you on a per function basis what it's doing. These are very strong hints for you to say, okay, well, that's the data clause that the compiler is using based on its analysis of this code. So this is very valuable information that is a guide for you to help go back in and look at your code, focus in on the particular data structures that the compiler thinks are worthy of giving you information, and go back in and analyze that yourself. So we're trying to raise your level of productivity here. Let the underlying system guide you, and pay particular attention to these data structures that are being moved around in the managed mode. It can also give you hints about collapsing loops and other kinds of things. So the output from compilers are extremely important to work through. And so we basically took the output from those and went back into the code. And first of all, in the main routine, before we get into that do while loop, we define the data region. And it's important to, where possible, only use the create when you need to. Copy in is moving the data, and then we also, there's a part where the data was being written back to the host. We had to insert an update clause to send the particular data structure, the MIG and the MIG1 data structures from the GPU back to the host. And we did that, we inserted that at the key place after the while loop where the update was needed. So this is the kinds of operations, the directives that we inserted in the code before the do loops, and the scope is over the whole course of the application. And then go in and also make use of other clauses like the present clause, so that it was already copied in to, you see here, the travel time table, T1, T2, and T were already copied to the GPU. Managed memory told you that it was copying in T1 and T2 and was copying out T, but analysis of this code says, no, we don't need to copy back out. We can tell it that we don't need to do the copy in. It's already present on the system. So that's where you can get some performance uplift, is by taking the output from the management memory and helping add the precise directives in here to pinpoint where the data needs to reside, and avoid these extra copies. And then this collapse option is here for adding more threads to the work items. So in a sense, when you collapse these two loops, you're doing the amount of work for NX times NZ threads. Higher occupancy, more work is a good thing for GPUs. All these are kinds of clues that you can get from the profiler as well as from the compiler output. And then we're looking at the data movement for the MIG2D, and we use the present clause in there as well. A very studious investigation of the code using that output and helping define those particular clauses. And the point being here also, you only really want to do copy and copy out when data changes. So that's something that the compiler may not understand the context, and by helping you pinpoint that data structure and looking at how it's being referenced, it helps give you ideas on how to define these data clauses. Finally, for resits, we also looked at the data that was already present, same kind of thing. We'll do a collapse and tell it, instead of copying the data in, it's already present on the GPU, no need to recopy. And same kinds of things. By the way, the delete happens when you leave scope, but again, using the output from the compiler and from the optimizer, then you go through an iterative process. So that now that you've inserted these data directives, now you compile, but you use it without the managed memory. You take that out and allow it to then give you information back about how the directives are. It's a way to double check to make sure what you told it to do, it works. So again, pay close attention to the output from this compilation stage. And then profile. Again, this is a profile-driven approach. So use PGPROF, and this is the output from it. Notice that now there's some interesting updates on the amount of time that's being spent in particular routines. We're getting some better distribution of work because we did some collapse. And most importantly, we're not having as many memory operations. So looking at the malloc managed That's completely gone now because we're not using managed memory. So that's what you would expect in the profiler, that it's not even present here. And then the other memory operations have reduced from quite a significant amount of time down to milliseconds of time. So this is a validation that we're on the right track. But the real validation comes with results. And results in this case show that initially we were at 218 seconds on one core. On the K40 GPU, we're down to 12 seconds using these data directives. Again, the lab associated with this will allow you to walk through this step by step. I see we're getting kind of close on time, so I'm going to march on and talk about this last stage, which is multi-core. Now that we've added the loop directives and did the parallelization, we optimized with data directives. We're set up to be able to go multi-core. And one option that you have for how do you want to take advantage of a multi-core environment? Well, one way is to use OpenMP. Another way is to actually go in and insert pthreads. And in those cases, you may have to do some extensive work to segregate out your data structures so that they're independent. But we've done the work here with adding OpenACC directives, not OpenMP. So we have OpenACC parallel directives and OpenACC data directives. The next thing we do is we tell it target multi-core, not Tesla. And it's not using managed here. There's no support for managed on the host. So this option is available with the PGI compilers. And you also have the ability with PGPROF to profile from the command line or from the GUI, as we described earlier. And you get some insight from that. It shows you that, what's going on behind the scenes, where the barriers are, what's going on. So this is actually a very, very compelling story. We didn't use OpenMP at all. Didn't use pthread. We stayed with OpenACC and data directives. Question is, what's the result? It's very interesting result. So 29 seconds is on a Haswell-based platform with 16 cores. So you have performance portability at this stage using OpenACC. In the lab, you'll be given a virtual instance from Amazon, and there'll only be 4 cores, and they won't be the higher end. They may have a different gigahertz rating. So you may not see this kind of performance uplift, but this really is a testament to taking some reasonable sized code that's meaningful for the oil and gas industry and targeting not only the GPU, but also the CPU. Now, remember, the model size here is pretty small. This is the dimension in the X dimension and the Y dimension, and for real seismic surveys, they're significantly larger. So these kinds of speed ups are very, very meaningful. To give you a sense, state-of-the-art systems that are GPU accelerated, workflows that used to take 28 days take 7 days now. So something on that order of magnitude involved here. But for purposes of illustration and for the lab, we kept it a pretty small sample size. And as you grow your sample size, there's other functions that may come in, and you use the same approach where you do a profile-driven approach based on your data sets. The question about deploy, well, it's only good if you get speed up if you get the right result. If you look here on the upper right, this is the model of the Earth that we're using here, this industry standard data set, and this is the output that's from the KIRCHHOFF migration that's for CPU baseline, which is identical to the one for OpenACC multi-core or for OpenACC GPU. So that's the primary material that I wanted to cover. Hopefully it gives you some energy and excitement to go try this similar kind of profile-driven approach and use the underlying system to help guide you through your process with your codes. There will be some homework. You can go to this website and register with the OpenACC promo code, and that will allow you to then go in and select the advanced profiling exercise or homework, and there's 4 different tasks that walk you through using the profiler with this KIRCHHOFF code with the smaller data set, and you can get hands-on experience. And also there's a resource here to give you more detail about if you don't already have the OpenACC Toolkit, where you can go get that and download it and run this on your environment. You can even get a free 90-day trial. So there's no reasons, no impediments, no hurdles for you to go try this and raise your knowledge and learn. See how this could apply in your environment. And finally, there's a set of slides here that talk about specifically where you go get the Seismic Unix package, how to build it using the PGI compilers, where you go get the data set, how to filter the data set, and basically do some processing to generate the synthetic data set from these models, and then the steps that are needed to actually invoke the application so that you can profile it, given various different parameters that are meaningful. You can adjust these parameters and get bigger run with help you understand scaling on a wider scale. Finally, a whole list of resources for you to go get more help in this area. Just a quick reminder, we're doing the office hours week from today, and we'll dive into more questions that you may have around the visual profiling. So I'll open it for questions. Julia, do you see any that, or Pat or Craig, anybody that are hot ones that I should pay attention to? I wasn't really looking at the chat as I was talking.
Yeah, so you have all the questions for you, and those that are specifically for PGI compiler, Craig and Pat already answered, and I posted them in their Q&A. So I think it's okay, we can reiterate them next time. There are really a lot of questions. Let's go through the actual code questions.
Okay. One that pops out to me is how does compare to OpenMP acceleration? And I think that when we kind of answered that by not having to do OpenMP. We use the tools to use the target multicore with OpenACC. I would anticipate that since we've added the data motion part of that with OpenACC, I would think you probably can get comparable or maybe better performance with OpenACC. To do this with OpenMP, you would have to go in and maybe re-architect some of your data structures to put them in separate bins to actually get acceleration with OpenMP. So there's significantly more code restructuring that might be necessary with OpenMP. In this case, we were very glad to see that the data directives, just staying at the directive level, we were able to get good performance back on multi-core. Let's see, our advantages with, you wanted me to look at code questions. Yeah, the initial code was not already parallelized, correct? Yes, it was not parallelized. If the code is already parallelized for MPI, well, it'd be as simple as adding the pragma loops. That's a great question. There's a Lattice-Boltzmann code that's very much a production code, and it's documented out there. I think we can send a link to that, Julia. But our DevTech team worked with this particular organization, and I don't remember the name, but here's what's going on. It's using MPI to do domain decomposition across system boundaries. And with the MPI rank that gets on a system, that MPI rank is associated with a particular GPU. On a system with PCI Express and a K80 today. Okay, so this is not some future state. This is real and now. So the MPI rank is associated with that GPU. Inside of that particular multiple nested for loop where they're doing computational fluid dynamics with Lattice-Boltzmann, there's multiple nested loop. They added the very same kinds of things we did, just the parallel directives around those loops. and they let the underlying system demand page. Now, remember, there's restrictions. It just so happens that all the data was allocated out of heap. There was no referencing from the GPU back to the CPU. Other restrictions were met in this case, but they're getting very nice linear scaling on real production code. You know, you could argue that the example that we gave here is from Seismic Unix and from university, but there are major corporations in the oil and gas industry that are using this code. So this is real, and it can absolutely work with MPI. Let's see. Can we use Fortran 95 with this? Yes. So I'm actually going to be writing a chapter, and there's some modeling code that's solving the wave equation, and there's a C version and a Fortran version, and these same principles apply there as well. What is the restrict keyword in Fortran? Don't have one. Craig or Pat can correct me on that, but the aliasing issue with C is one of the reasons to add the restrict keywords. Okay, yeah, so the question also was, it would be great to see the full code. The link that's in that we gave you for your homework exercise, you can go download this yourself and see this code. Where is that? Right here. You can go to this site. We in this case use 4.3. We're version 8. There's a version 4.4. Feel free to use the latest version. In fact, that's recommended is to get the absolute latest version. Question about, is OpenACC compatible with CUDA code? Yes. I will use the name here. Total is a major oil company. They have been strong proponents for OpenACC, and the reason I can use their name is because they've spoken multiple times at many events, most recently at our GPU Technology Conference last month. And they shared how they used OpenACC on our Titan supercomputer. And they were focused on what's called a one-way wave equation migration. Like I said earlier, there's many different types of migration codes that are out there. In the one-way wave equation, they're using some spectral code. So they actually used our FFT libraries in addition to OpenACC, and through their profile-driven approach, identified one particular area that was troublesome was a transpose. And our compiler didn't do a good job managing that, and it had to be conservative. So they went in and inserted in very small portion of their code a CUDA element that would do the transpose using CUDA calls. So here we have a mixture, one-way wave equation migration that's using OpenACC, it's using libraries, cuFFT, and in a small, very isolated portion, the non-portable CUDA. But the reason they did that is because it got a really good uplift in that. And guess what? That knowledge that is imparted to our compiler team to help try to improve our tools in that space. But the other thing they did is they actually used as much of the Titan supercomputer as possible on an extremely large data set. Think of something massive survey that you might have off the Gulf of Mexico, off the border of the U.S. And they were very pleased at the level of performance they were able to achieve and using the entire thing and using compiler directives, a combination of libraries and native environments. Julia, I see that we're at the top of the hour. What do we do next?
I see that there are a lot of questions. If you have another 5 minutes, let's spend this time answering questions, if you don't mind.
Okay. Let's see, I better scroll down. Yeah, the question about how GPU compares to CPU, not just one core. I hopefully answered that with the multi-core option. Any pragma ACC routine used in this code? No, not in this code. In the data region, when's the advantage of the managed memory if we specify what data we move? Are there some other data being moved automatically by the managed memory that I missed from the slide? So the point here is you use the managed memory without data directives, and then take the output from the compiler and the profiler and help for managed option and help use that to define the data directives within the code. Is it a good idea to use collapse in general? I can see situations where it probably won't improve anything. Yeah, that's a good question. There's a trial and error that's probably necessary there. It's easy enough to do that. And yet occupancy is a tricky thing in that sometimes more occupancy doesn't necessarily lead to better performance because there are other resources that might be limiting. So it's something that's easy enough to try and see what kind of performance levels you get. What's the difference between OpenMPI and OpenACC? OpenMPI is the MPI implementation. There's also an mVappage implementation, and it can work in conjunction with OpenACC, as I described earlier. How does the compiler retrieve where present variables are on the CPU? Is that done at runtime? Okay, what we did there is we actually used we were focused just on the GPU aspect of it, get the best performance on GPU, and then we simply just turned the switch on to multi-core, and behind the scenes, the compilers did the right thing. We were very pleased at that process. Like to know more about complex routine nested function calls? Yes, that's a good question, and deep copy operations and all those are important. Maybe we can work with you to get an example case and build another lab or build another session. Can I arbitrarily use a Fortran compiler in a program calling CUDA with OpenACC? Yeah, you can mix and match CUDA libraries in OpenACC. What would be the impact of using multi-CPU and GPU acceleration together? That's absolutely used. Again, the example I used with MPI. We also have this notion of CUDA streams, and you can define multiple streams to multiple devices. State-of-the-art in Seismic is to use the host and the device. It is asynchronous, and so control comes back to the host. And you can stream data independently to each GPU, and each GPU can share data in peer-to-peer fashion with our APIs. That's using some of the CUDA stuff. To implement that same kind of capability, you might have to use async operations. Let's see, can we combine OpenACC with cuBLAS? Yes. The question is, how would we do parallel loops and BLAS calls on for multi-core? That's a good distinction that you would need to actually probably put some if-def calls in there to get the support for using the BLAS functions that are available on the host side.
Okay. Thanks, Ty, a lot.
Okay.
Yeah, let's
Sure.
leave the rest for the office hours. Thanks a lot, guys, for submitting questions, and the questions are still coming in. I guess we can run indefinitely. We will be covering a lot about on Visual Profiler in the next session, and I see there are a lot of questions about running the code on both CPU and the GPU. We will cover that as well, and we'll see what other questions are showing up. And if you have questions kind of offline, you can send them to openacc@nvidia.com. We'll be monitoring that email, and we'll add your questions to our office hours. And a reminder, so there is a lot of resources available online. You can check it out. So we put together a few links. There is also a course that we did last fall that has a lot of information as well. So you can reference those presentations. There is a Q&A, transcripted, PowerPoints available, and the recording. Homework is available for you as well, so Ty spent quite some time to create this lab for you. Again, if you have questions, send an email to openacc@nvidia.com. All the presentations have been recorded. We will post it to the Advanced OpenACC course page. We'll try to do it today, but let's shoot for tomorrow to have it available online for you guys. And one question was about Xeon support for OpenACC. It is in the roadmap. We do plan to add it towards the end of the year. So we'll keep you posted on that. And again, send your questions. The next class is going to be office hour on May 26th, same time at 9 a.m. Pacific time. Again, don't forget to join it. We will be answering as many questions as we can at that point of time. And thanks a lot for participation. Really appreciate your interest, and we're happy that you're enjoying the course. Thanks a lot.